So in a lot of the further maths past paper questions about polynomials, they ask us to calculate Sn, where Sn is defined as follows. If p of z equals 0 is the polynomial equation with roots r1 to rm, then Sn is the sum of those roots, each one to the power of n. There are multiple ways you can find Sn, and often the quickest way is to actually substitute the roots of the polynomial equation into the equation itself. So we'll take a look at that soon. So here's a nice example to play around with. Suppose z cubed minus z minus 1 equals 0 has roots alpha, beta, and gamma. We can immediately find S3, which is alpha cubed plus beta cubed plus gamma cubed, by substituting these values into the polynomial equation. So first of all, we can actually quickly see that alpha plus beta plus gamma is equal to 0, because there is no z squared part of this cubic equation. The z squared coefficient is 0. So alpha plus beta plus gamma is equal to 0. Now, since alpha, beta, and gamma are all roots to this equation, we also know that alpha cubed minus alpha minus 1 equals 0, beta cubed minus beta minus 1 equals 0, and gamma cubed minus gamma minus 1 equals 0. And therefore, simply adding these things up, we get alpha cubed plus beta cubed plus gamma cubed minus alpha plus beta plus gamma, and then minus 3 equals 0. And since alpha plus beta plus gamma equals 0 anyway, we get alpha cubed plus beta cubed plus gamma cubed, which is S3, is equal to 3. Now we can also get S2 by looking at the sum of the roots squared. So, by the way, we also know, because of this polynomial equation, we know that the sum of alpha beta, which is the sum of the product of any two of the roots, this one is negative 1, because it should be c over a. In this case, c is negative 1. Alright, and so therefore, considering the sum of, we know the sum of alpha squared is actually equal to the sum of alpha squared plus 2 times the sum of alpha beta. Alright, so that means that S2, which is the sum of alpha, well, S2 is this one, so it's alpha squared plus beta squared plus gamma squared. It's equal to the sum of alpha squared, which is 0, plus 2 times the sum of alpha beta, which is negative 1. So in this case, it's 0 minus negative 2, so 2. Okay, and once we have S2, we can also rearrange the equation to, well, just divide this thing by z. We get z squared minus 1 over z is equal to 0. And that quickly allows us to calculate s negative 1, because substituting the roots alpha, beta, gamma into this equation gives us alpha squared minus 1 over alpha equals 0, beta squared minus 1 over beta equals 0, and gamma squared minus 1 over gamma equals 0. And so adding those three equations together just gives us S2 minus 3 minus S1 equals 0. Sorry, not S1. S negative 1 equals 0. And since we know that S2 is 2, we have S negative 1 is equal to 2 minus 3, which is negative 1. And I said, as an exercise, play around with this thing and see what other values of Sn you can find pretty quickly by making those substitutions or using whatever other techniques you like. Just for example, if you go ahead and divide this thing by z again, you get z minus 1 over z minus 1 over z squared equals 0. And so if you substitute in alpha, beta, and gamma again into this equation, you can get S1 minus S negative 1 minus S negative 2 equals 0. So that's from substituting in alpha, beta, and gamma to this equation and then adding them all together. And this one here is S1, so we know S1 equals 0, and we know S negative 1 turns out is negative 1, and so that's, well, adding S negative 2 to both sides, we can see that S negative 2 is equal to 1, and of course S negative 2 is 1 over alpha squared plus 1 over beta squared plus 1 over gamma squared. So yeah, the point of this little section really is just to remind you, if you have a polynomial equation and you have the roots of that equation, you can actually substitute the roots into the equation and the equation should still be true. And then you can make use of it in ways, well, here's an example of a way that you can make use of that.